announcements. As always, you have homework due tonight. Another homework is already posted. This homework is on optimization, which is like my favorite part of all of math. And so I included lots of, at least to me, interesting problems on all kinds of different things. For example, one question that people ask, especially in economics, is sometimes you want your rocket to land in the right place and at the right time, and you don't want to have to trade off. Like it's like the Tina Fey optimization. You want to have it all. And to that end, you might ask a question of, can you solve a problem with multi-objective optimization? And what does that mean? So you'll walk through a couple simple models for that. You can blame some folks that stuck around after class a couple days ago to ask about linear programming for another problem on your problem set, and then the rest of it is and so on. Right, your midterms are graded. The class average was kind of low, but that's okay, because it was a hard exam and I curved things. So you're going to see your exam and you're going to feel bad for about 18 seconds, and then I want you to put it down and remember that Justin's a nice guy and it's going to be okay. Alright, so everybody take a big, deep breath. It's going to be fine. I know this is a hard class. And if you really, and we'll post like a histogram, and if you really are in the bottom part of the histogram, come see me, and I'll try and help you out so that doesn't happen again. Cool? That's my job, and I'm pretty dedicated to making sure that doesn't, that nobody is just totally drowning in 205. Right, homework that, and I posted a little announcement on Piazza. If you're interested, and I will not offer extra credit because I don't want any conflict of whatever the heck. I have to give a talk at a faculty lunch tomorrow on my own research, which happens to be very closely related to what we do in 205. And so I needed a place to practice, and I'm going to do it here, and you're welcome to stay and provide criticism, take out all of your passive angst with your instructor in the meantime, or not. So it's all good. I'll give you cookies or take you to coffee or something if it's there. All right, any procedural questions or anything before we get started for the day? We got lots of material, as always. Going once, going twice. Cool. All right. So in our last lecture, we stopped at the crowning achievement of constrained optimization, which are the KKT or Karush-Kuhn-Tucker conditions for an optimization. Right? You can sort of think of there being like kind of a hierarchy of more and more annoying versions of calculus that have to happen as you solve more and more complicated optimizations. Right? So in high school, when you wanted to optimize a function of a single variable, you took the derivative, you set it to 0, you were done. And probably a couple of years ago in Math 51, you took the gradient, set that equal to 0, you were done. Then you added equality constraints, right? So we had to use this Lagrange multiplier trick. And finally, if you want inequality constraints, we came up with this whole list of things that has to happen when you're at least an optimal point to first order. And these are very important conditions. They might not look humongously intuitive, but in fact they are. You should revisit our proof from last time of the KKT conditions to make sure you have some intuition for what each of these 4 bullet points is telling you about life. Cool? So in the homework you're going to get some practice with computing KKT conditions, at least for a linear program. And you're going to prove a really important theorem. Don't worry, it's only a couple lines. From linear programming, which basically says there are 2 linear programs called the primal and the dual, and that you can actually use either of these 2 linear programs to solve the other. And in fact, algorithms for optimizing linear programs are completely based on this fact. And I was thinking, I think maybe for your next little coding challenge, which I'll give you more time for, maybe you'll actually derive some version of the simplex algorithm and give it a try, because it's very important. Anyway. So what I didn't tell you how to do was how to actually do an optimization, right? We now know how to characterize, optimal points, and sort of we have a first order condition for where we think critical points are, but we need to find them. And algorithms for doing this, unsurprisingly, are very difficult because you're solving like root finding, optimization, and finding feasible points all at the same time. But there are a couple that are very important, and we're going to cover them at a very high level, because this is not the focus of 205, but it's important for you to kind of know that they exist, and that you can get client to these things. And then we're going to move on to conjugate gradients, which we will do in excruciating detail, because it is important and well within our grasp at this point. Cool. So, one of the main algorithms for doing constrained optimization, remember that the basic form, why am I carrying around like 20 markers? The basic form of an optimization looks like minimize f of x such that, yeah, st means such that, by the way. And sometimes I put a little subscript next to the minimize. If you haven't seen that before, you can think of that as moving that downstairs next to such that. Yeah, such that I think I use g of x equals 0, right? And this might output a vector, and h of x is greater than or equal to 0. Yeah? That's the problem we're trying to solve. And lots of problems when you're in this way. So one sort of reasonable, right, we keep returning to the same like 5 tricks here. And one of the tricks that we've used for optimization is this idea of Newton's method, right? Where you take your function, you approximate it with an easier one, right? For optimization, we approximate it with a quadratic. And then you minimize that thing. And then you say, okay, well, if my function were actually quadratic, I'd be done. But in fact, it's not, so now I'm just going to iterate and keep approximating my function and keep minimizing this approximation, right? That's the high-level idea of what Newton's method's doing. Yeah? Yeah? Cool. Right, so we can do the same thing for constrained optimization. And in this case, we have to approximate not only the objective, but also the constraints. And this leads to a method called sequential quadratic programming, or SQP, which is, by the way, these are more or less state-of-the-art methods. These are things people use in practice. Right? So if you'll look at what SQP is doing, basically, remember that the Hessian h sub f is like the second derivative of my function? Right? So this thing next to the minimization is like a second derivative sort of quadratic approximation of f. And then I'm also going to approximate my equality and inequality conditions, yeah, g and h. And they can just be linear. So I have a second order approximation of f and a first order approximation of g and h. And then what SQP does is it simply optimizes this thing, and then does again, and again, and again, and again. And by the way, you can still use all of our favorite Hessian approximations and stuff that we've talked about in previous lectures. Or not, if you happen to know the Hessian in closed form. One particularly nice thing happens if you only have equality constraints. And I do think it's worth working this out, just so you can see that, in fact, this isn't any worse than Newton's method without constraints. So for now, suppose that we just have minimizing f such that g is 0, so no inequality. We'll come back to that in a second. Well, how do you think I'm going to minimize this function, or characterize its minimum? Lagrange multipliers, yeah? It's like the only thing we know how to do. So let's do that. So we have a function lambda, right? And he's a function of the point we're trying to find, and also now the Lagrange multipliers. And it's very simple, right? Just equals f of x minus lambda transpose g s. You know, hopefully you all agree with me by now that this is the Lagrange multiplier of the function, but you shouldn't, because now remember that really what we're solving is this sequential quadratic programming problem. So instead of doing that, we're going to find the Lagrange multipliers of this system. Yeah? Slightly different. So, in particular, is it okay if I erase this? So this is what we'd like to solve, but we can't, so we're going to approximate him. And then what happens? Well, in fact, now let's plug it in. So this is a search for the direction, by the way. So we subtracted off x k. So you get 1/2 d transpose h. Is it okay if I just call the Hessian h to save some writing? Times d, right? Plus grad f dot d plus, and then I don't really need the constant term because I'm optimizing the function. Constant shift doesn't do anything. So I'm going to ignore. In fact, I already did that upstairs, right? There's some displacement there. Okay. Plus the Lagrange multiplier times g at xk, right, as your current iterative, plus dg times. Right. This is the Lagrange multiplier thing of this optimization, assuming there's no h. Yeah. Okay. So what do you think I'm going to do? Well, I'm going to differentiate. Oh, and by the way, I guess now we're searching direction. So I'm going to differentiate this guy with respect to d, and what comes out is a really nice expression, right? So you're going to get, right, you want to set the derivative equal to 0, and in the end you're going to get that this is the Hessian times d plus grad f at xk, right, which comes from this term here, plus the Jacobian of g transpose times your Lagrange multipliers. You can trust me that it comes out. You kind of know it because this is a constant, And this thing, now you get the Jacobian, but we really want, the unknowns to be in the same place for each of these. Yeah? Okay, so I'm going to write this form in a slightly different form. So what are our constants here? And what's known and what's unknown? Well, we know this guy, and we know this guy. We know this guy. We don't know d, and we don't know lambda. Yeah? So in particular, if we move all the unknowns to one side and all the knowns to the other, then we can write this as sort of a block matrix system. And let's see if I can do this right. Where you have d and lambda are your two unknowns. Yeah? And what's next to d? The Hessian, right? Yeah, Hessian, d, g transpose. And then, that's encoding exactly this linear relationship right here, okay? Hessian times d plus dg transpose times lambda equals minus grad f. Yeah? Oh, what else do we know? Well, we know that the equality condition just holds, right? We know that grad g dot de plus g dot xk equals 0, right? By definition. So if we plug that in here, what happens? Well, in the end, we get dg, right? So this is this guy times g equals minus g dot xk. This is a linear system of equations, right? So if I want to do sequential quadratic programming, and I have equality constraints, this is no harder than just Newton's method, just a bunch of linear cells, just like before. So in fact, it's actually a pretty reasonable thing. Now what happens when I add these inequality conditions? Well, I'm a little bit hosed. Right? If I look at the KKT conditions of this guy, they're not particularly nice. And so we have to use a couple different strategies to be able to solve that. In particular, so here's the equality thing. You can approximate the Hessian if you like. One common trick is that sometimes if your Hessian is a little bit wrong, right, you might overestimate how far you should be moving. So one common thing people do is they simply scale down how far you're allowed to walk to a smaller step. And this way you don't go totally crazy. So if we want to add inequality constraints, there are a couple sort of ideas from a high level of how you might pull this off. So for sort of medium scale problems, you could use something called an active set method. So remember, there are two types of constraints at the optimal point, right? There are active ones and inactive ones. We remember what this means? Basically, when you have an inequality constraint, right, h of x is greater than or equal to 0, this thing I x'd out here, then you have two cases. Either h of x is strictly greater than 0, or it's actually equal to 0. Yeah? The second case is called an active constraint, and the first case is called an inactive constraint. And so one thing that an optimization tool could do would be to simply keep a list of which constraints it thinks are active and inactive, right? And why do that? Well, you can remove the inactive constraints, and you can set the active constraints with an equality sign instead of an inequality, yeah? Well, in that case, you're back to this iteration, right? So an active set method will decide on the active set of constraints, solve them as if they were equality constraints, look at one coming out and see which constraints are violated, right? Add those to the active set and then try again. Yeah? It's actually pretty straightforward, even if the implementation is kind of messy. Right. This chair is in the way. Okay. An alternative approach, which is actually becoming very popular, is something called the barrier method. And the idea here is, for example, let's say we want to optimize f of x such that g of x is equal to 0. Right? One way that I could do that would be to define a new energy called f sub rho, which is equal to f of x plus rho times g of x squared. Right? Now the minimum of this thing is not the minimum of f anymore. But what happens as rho gets really, really big? Well, when rho gets really big, g wants to be 0. Right? You see that? Because you're weighting this term as big as possible. Right? So what a barrier method does is it defines this energy f sub rho, which is now unconstrained, and we have all of these nice unconstrained methods for optimization. Remember BFGS, Newton, and so on. Right? So we can run an unconstrained optimization on f sub rho, and if we're lucky, then it'll more or less satisfy g equals 0, and we're done. Right? Because if g equals 0, then f sub rho is equal to f of x again. Right? So not only did you minimize f, you also satisfy your constraint. And if that's not the case, then we crank up rho and we try again, using the previous iterate as sort of an initial guess of our solution. Yeah? Does This is called a barrier method. Now, a reasonable question somebody might ask would be, why not just do barrier method once with one ginormous value of rho? Right? And certainly, in theory, this should work, right? And the answer is that if you look at, for example, the iterates of Newton's method, right? Each time you invert a matrix, what do you think is going to happen to that matrix as rho gets really big? We only know one thing that can go wrong with matrices. It's going to look really close to singular. In fact, the condition number is going to be really horrible. And why is that? Well, we sort of expect the space of points where g of x is equal to 0 to not just be some point somewhere, but to be a nice spread out thing, right? Otherwise, you could just solve g of x equals 0 without optimizing f at all. Yeah? So, because you have this big spread out different set of points, all of which satisfy g equals 0, right? Well, that's exactly the kind of case where if you think of the linear approximation, you have this plane that's running into 0 in all kinds of different places. That makes your matrix uninvertible, right? So as you crank up rho, this thing becomes harder and harder to solve, or to optimize, right? So what the barrier method does is it wants to use sort of the minimum possible rho that makes you satisfy the constraints within some tolerance in the end. Now, one question you should probably ask is, okay, well, we also talked about inequality constraints. And it turns out these also work in the barrier method. And what you do is you simply, you think about functions that get really, really steep as you get close to 0. Right? And so what the barrier method does, so for example, right, if we plot f of x equals 1 over x, right? Obviously it looks like that, right? So if I put g of x into this thing, then when g of x gets close to 0, right, my energy term gets really big and it's going to want to push it back out, right? So basically, the barrier method with an inequality constraint is you just have to be clever about the additional terms that you add to your energy. So the barrier method is really attractive. It's very easy to implement. It's sort of reasonable, right? You just crank up energy terms that measure the constraints, because that's what's really important. And then once you satisfy those, then secondarily you also want to minimize your energy. But you have to be very careful about that choice of rho because it affects the conditioning and convergence of your method. Cool. All right. So unfortunately, we don't have time in class. I had to jettison a little bit of material. So all of these optimizations we talked about so far are guaranteed under pretty weak conditions to give you some local optimum of my energy, right? But we can't make too many global statements because your function f could be wild and crazy, right? It could be dipping every which way and maybe even just goes to minus infinity somewhere. And somehow we haven't developed a sufficient theory to say when, for example, BFGS is guaranteed to give us this global optimum as opposed to this little divot here in the energy. Right? And theorems about this are very weak and difficult to apply. But there's one exception to this rule, which is convex functions. Right? Remember, a convex function is bowl-shaped. It's basically the picture you should have in mind. And to formalize bowl-shaped, what you do is you take 2 points and you draw a line between them, and your function has to live underneath that line. There's a definition of this in the course notes. But basically, if you optimize a convex function, it is guaranteed to have a single minimum. It makes sense, because bowls don't have more than one divot at the bottom. Yeah? And in fact, if you optimize a convex function with convex constraints, what is a convex constraint? It's one where a set of feasible points satisfies that if I take 2 feasible points and draw a line between them, that entire line is also feasible. I suppose this is not a convex set because of that. But yeah, if you optimize a convex function with convex constraints, in that case you are guaranteed to have a unique minimum, and you're guaranteed that methods like the barrier method tend to converge very well. And this is actually, there's a professor at Stanford who is famous for convex optimization. His name, his first name I forgot, Stephen, I guess, Stephen Boyd, who teaches an entire course on this, and it is highly recommended by me. It's a very well thought out class. In fact, I think it's on, it's going to be on Coursera or something, so you should take a watch. Because convex optimization shows up all the time. You'll see that in your homework. Cool. All right, so that's all we're going to say about optimization in 205A. You'll see on your homework I'm mostly concerned that you guys are sort of clients of optimization tools rather than knowing the ins and outs of all of the convergence details and things of these iterative schemes, because honestly they're very difficult. and this is a survey class. But that's okay, because basically the things you should get out of our lectures on this stuff are you shouldn't abandon all hope just because you can't squeeze your function into a linear form. That in fact, lots of nonlinear problems are solvable, and what you should do is simply experiment with a lot of this machinery, right? And all it needs is like a function, its first derivative, and maybe its Hessian. Throw it in there and see what happens. And oftentimes you'll be surprised with how well these methods work. Fair enough? Cool. All right, are there any questions about optimization before we dive back into our favorite problem in 205? No? Good, because this stuff is hard. All right. I'm trying to actually, I made this thing. Okay. Full screen. Cool. So I get the impression that we didn't get a chance to look closely at conjugate gradients documents on the internet before class. No? Okay. So that's a shame. You should read through. I provided links. In particular, I provided a link to a document by Jonathan Shuchuk. I mentioned this last class. It's like the conjugate gradients method without the agonizing pain, I believe is the title of the document. And well, I don't agree that we should at all associate the words conjugate gradient with pain. Shuchuk does a very good job of very slowly walking through at least his derivation of the conjugate gradients method and drawing pictures at each step of the way, which is useful, especially if you're kind of a visual learner. And he also reviews like eigenvalue methods and all these other things, so it's good review for 205. That said, his document is about 73 pages long to cover an algorithm that fits in 4 lines. So in the interest of your time and my own, we're going to follow a slightly different path that's going to get us to conjugate gradients a little bit faster, but with fewer graphs. So there's a trade-off there, and the document is there if you prefer his. So there are any number of derivations of conjugate gradients that you can use, and you should just search for the one you like, and just read a bunch, because the more you read, the better intuition you'll get. To me, the derivation of Wikipedia, by the way, which seems to be the tool of choice in 205, is basically unreadable. So I would be very careful. It's like written for like a PhD student in applied math. I can barely follow it. Anyway, so what's our favorite problem in CS 205A? It's solving AX equals B, and in fact our even more favorite problem for AX equals B is when A is symmetric and positive definite. Right? And so the conjugate gradients algorithm is an option for doing exactly that. By the way, we already have an algorithm for solving AX equals B when A is positive definite and symmetric. Do you remember what that is? It was on your midterm? Cholesky factorization. Yes, but we have this problem, which is Cholesky induces fill, right? So if I have, for example, a very sparse matrix, Cholesky factorization could be a bad option because it might have a very dense Cholesky factorization even though the matrix is sparse. So, let's say that I have an n by n matrix A, right? Just a little bit of a review. How much time, like in a big O way, does it take to do Gaussian elimination on A? N cubed, yeah. This is an n cubed algorithm. Hopefully this is reviewed by now. And that can be a very long time if n is large. We don't like n cubed, not so good. So there's a common case that we're going to see. We've already seen some examples of this, and in fact when we talk about differential equations in 2 weeks, we're going to see lots of examples of this, where a matrix is easy to apply and hard to invert. Now what do I mean by this? So first of all, when I use the word apply, when I'm talking about a matrix, what I mean is multiply. Okay, so these are going to be synonymous with one another. And in particular, sometimes matrices are very easy to multiply by vectors, even if they're difficult to solve AX equals B. So a canonical example, unfortunately one to which conjugate gradients does not apply, but we'll come back to that in a while, is this matrix here. 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, and so on. Okay? So this is a lower triangular matrix, and it's made of all ones. Now, if I want to multiply this matrix by a vector, and I write it in this form, how much time does it take? Well, obviously it takes n squared time, yeah? Because I have to, how do I do matrix vector multiplication? I do it like that, yeah? And I'm iterating over the whole matrix. But what do we notice? And we're going to multiply this by x1 to xn, yeah? So what's going to be the output? It's going to be x1 plus x2, x1 plus x2 plus x3, and so on. Right? Hopefully we can see that. So in fact, we can multiply this vector by this matrix in order n time, right? Because this number is equal to this, or rather this number is equal to that number plus this guy, right? There's a nice, sort of, just a nice, like I said, you can even write it out, right? yi equals yi minus 1 plus xi, yeah? Where this is y. So in this case, this matrix is easy to apply, but it's not clear what its inverse is. Well, no, so it's sort of clear what its inverse is, but there are other examples for which that's not the case, right? And so, in this case, when we do Gaussian elimination on this matrix, somehow we'd like to take advantage of this fact, right? We know more about this matrix than something we've used. Another example when matrices are easy to apply but difficult to invert is when they're sparse, right? So remember, sparse, our vocabulary word for matrix is mostly 0. So we don't have to store a matrix as like a, a two-dimensional array. One thing we can do is simply store a list of the non-zero values in my matrix, right? Perfectly legitimate way to store a sparse matrix. And in that case, matrix vector multiplication takes place in time proportional to the number of non-zeros in my matrix, yeah? Well, that could be considerably less than n squared time, right? For example, if I multiply by the identity matrix, it's certainly n time, yeah? And so in this case, this is the conjugate gradients algorithm is tuned for this bizarre case where you have a matrix that's easy to apply, easy to multiply, but difficult to invert. Hopefully I've convinced you that this is a useful thing to study. But thankfully, over the last 2 weeks, we've developed a new philosophy in CS205A. In fact, over the last several weeks, starting with eigenvectors, right? Which is that some problems we can't expect to solve in closed form. Right? So when we did Gaussian elimination on a matrix, we knew that like if we had infinite precision arithmetic on our computer and all that, the thing that came out was actually the honest-to-goodness solution to AX equals B. Right? But when I run, for example, eigenvalue iteration or BFGS or Newton's method or what have you, I get this sequence of xi's, right, that are approximating a root or a minimum and getting closer and closer and closer to that minimum, but they might not ever actually touch it. You see that? It's a little bit different. And so we'd like to apply that philosophy to our favorite problem of solving AX equals B when A is square, symmetric, and positive. Yeah? By the way, later on we're going to relax those conditions a little bit. Cool. Yeah, what do you know? That's today's one. Okay. Alright, so as usual, we're going to take, right, sort of another unifying theme in this class is that we like to use variational math. And hopefully, if you got this question wrong on your midterm, it is now burned in your brain that a variational problem is simply like when you express a problem that you're trying to solve by minimizing some energy. Right? So far in CS205A, we've talked about solving, for example, least squares in a linear system as minimizing one energy, which is not on the slides right now. Right? What is that energy? It's simply the norm of AX minus b, for example, 2 squared. Yeah? This works for, at least for overdetermined and completely determined systems. Right? But somehow, right, if we multiply this guy out, we're going to get A transpose A, and we know his conditioning is a little weird. So if we can avoid that, we'd like to. And thankfully, at least when A is symmetric and positive definite, we can write an alternative optimization, which is the one I've shown you on the board. So in fact, we're going to call this thing, I guess I didn't say so explicitly, we're going to define this to be f of x, and he's going to be equal to 1/2 x transpose ax minus b transpose x plus, and then if you want, you can add any constant you want. It's not going to affect the minimum. Yeah. So we put that there for fun, but the c is going to vanish the second that we do anything interesting. Cool? And this is a variational viewpoint on what it means to solve AX equals B. In particular, what's going to happen if we try and do, our favorite, in fact, remember we have our hierarchy, we set the gradient equal to 0, do Lagrange multipliers, or do KKT conditions. Which one do we need to do to minimize F? Yeah, just set the gradient to 0, there are no constraints here. particular, what is the gradient of f? Well, because A is symmetric, in fact, the gradient of this term is nothing more than ax. When A is not symmetric, that's not the case anymore. This is going to look like the average of A and A transpose, right? Minus B. Yeah, so in fact, it's pretty easy to see that when you minimize f of x, that it's the same as solving A is equals B. Cool? By the way, I haven't explicitly proven to you that this is a minimum as opposed to a maximum or something else. And that follows from A being positive definite. Right, so we're going to need all of our pieces here. Cool. So, in our, I think 2 lectures ago, we discussed a strategy for optimization called gradient descent. Right? And our basic observation was that if I'm standing at my toes and I'm looking at the values of some function f, never mind if f takes this form or any other form, and I take its gradient, the gradient points uphill. Right? It points in the direction that f increases the most. By the way, this is easy to get wrong. The gradient direction, despite the name gradient descent, points in the direction of greatest ascent. The negative gradient, however, points in the direction of greatest descent. Yeah? So I look at my toes, I compute the gradient, I turn around 180 degrees and I start walking in that direction. Then I compute another gradient, I turn in this new minus direction and keep going. Yeah? Gradient descent. World's easiest algorithm for minimizing the function. And in our homework you'll see a couple details that I left out and that they're actually quite important. But anyway, so the search direction for gradient descent is nothing more than minus the gradient of f. And as we just computed here, the gradient of f is ax minus b. So if we're trying to minimize this function f in particular, then I want to step in b minus ax direction. Yeah? And by the way, this direction has a name. It's called the residual. You probably remember this from high school algebra for literally solving ax equals b for scalars ax and b. Yeah. Cool. So then it's not enough to just compute the search direction, we actually have to do something, and in particular we step a little bit in the gradient direction, right? So we're going to take our previous approximation of where the minimum is, and this is the search direction, we're going to step some amount in that direction. Now a problem that I mentioned in previous lectures that's kind of challenging is, what value of alpha k do I actually choose? Right? And why is that challenging? Well, in some ways, I've reduced this down to a one-dimensional minimization problem. Right? Now I'm standing at xk minus 1, I have a direction, right, this d vector in front of me, and I'm taking a slice through my optimization objective, right? There's a bunch of different values that I'm trying to minimize, and along this line I want to find the position of the minimum possible value. That's still an optimization problem, and there's still something to solve, and in many cases that's not a trivial thing to have to solve, right? So there are all these strategies called line search that are all about how do you choose this parameter alpha in a given iteration k. By the way, if you're in machine learning, usually you just take alpha and be some constant you make up and you call it the learning rate. But you do have to be a little bit careful about that. Right. So let's go in a little bit more detail. Remember, what did we do? We were going to say, okay, we're going to restrict ourselves to looking along this line. Right? I'm standing at a point x, and now I'm moving in some search direction d. And I have the option of scaling it by any alpha, and I want to find the minimum over all possible directions I can walk. Yeah? Or not directions, but distances rather.